Let me restart the entire system. I don't know why. I can see some lights on throughout the projector there, but there's nothing projected on the screen. Or maybe let's try to turn off the light first. Oh, it has nothing to do with the lights. I've tried all the options, but it doesn't seem to work. Let's try to restart the projector. Oh, it finally works. Please wait 2 more minutes. I think someone unplugged some wires here, so finally it works. So here's today's outline. We are going to cover some announcements first, and we are going to do some recap and have a look at of our roadmap, and we will learn more about some SQL queries, including bags, sets, the operators, more about grouping, and also some abstraction for complex queries. And we will also learn about SQL functions. You will be using SQL functions for your assignment 1. So for assignment 1, for the first announcement, you will have to do your quiz 3 this week. And in the next week, you don't have any quiz, so you can focus on your assignment. And for quiz 2, the average score is actually a bit lower than quiz 1. And when I see the trend of quiz scores in previous terms, it's like going all the way down for the quizzes. But still, you are scoring higher than previous terms, so good job, class. So the second announcement is about the assignment. I believe most of you have received the email. So the specifications, and sorry for the delay, we have encountered some technical issues, just like today's lecture. So the specifications will be released by this Wednesday, and the submission should be before 10 p.m. Note that it's not midnight, and 10 p.m. on 22nd March, which is the Friday of week 6. So you are essentially given more time for assignment 1. And assignment 1 will be using SQL views plus SQL functions and PGSQL functions. So again, since you have given more time, so you can actually use whatever means you want to finish the assignment. However, I do encourage you to do it on your own, because the purpose is for you to practice, for you to master the knowledge. So that's the second announcement. And the third one is that we are hosting some help sessions this week. So if you have problems setting up your VXDB2 account, or if you can, because since the data and the schema has already been released for assignment 1, you can try it. And if you have encountered any problems with the released material, you can go to the help sessions. So that's all about the announcements, and let's come to roadmap and recap. So in our last lecture, we have covered views in SQL. So do you still remember the syntax for creating views? So the syntax is very similar to the keyword used is the same as creating a table. So the keyword is create. You can create a view as a query. So the other keyword is as here. And talking about tables, so what's the difference between views and tables, and what's the relation between views and tables? Actually, views can be considered as references to tables. So it's very similar to pointers in C language. So if we update the data through the view, the actual data in the table, in the associated table, is also updated. And if we modify the content of the stored data in the table, the result when we query the view is also affected. So this is how it works. And dropping a view doesn't affect the content of the table. And there are some restrictions for updating the view. Actually, there are 3 different types of restrictions. And I hope you could remember that. We won't cover too much of details here. And lastly, we also covered materialized view. So most of the views are stored as a virtual concept. It's just a reference to the original data. And materialized view is actually stored in the system, and it allows us to access the content of the views faster. And the syntax for creating a materialized view is create materialized, and then followed by the normal syntax of creating a normal view. And that's all about the materialized view. And our second main topic in the last lecture is multi-table queries. So the key word here is, or the key concept here is join. So we have different types of join. We have inner join, which is to match the tuple on both sides of the tables, and this is called inner join. And we have three different types of outer join. We have left join, we have right join, we have full join. So for left and right join, the order of the tables matter. So that's about joins and their differences and properties. So sometimes when we join different tables together, we may encounter name clashes because attributes, different tables could have attributes with the same names. So when we join them together, when we put them in one single SQL query, we need to resolve the clashes of names. And what we normally do is that we could use the table dot attribute notation here to avoid the clashes. And sometimes we have to use one table more than once in one single SQL query. And in that case, we assign each instance of that table an alias or a name. So that's how we deal with name clashes. And that's about what we have done. And our plan is, let's try to go through our plan again. And so our plan is we learn more SQL querying features today, plus SQL functions today. Let's try to cover as much as possible. And then we learn PL, PG SQL on Thursday. And that will be enough for you to do your assignment 1. And actually, according to our outline, course outline, we have to learn this in week 5. But I think it's a bit, because most of the assignment 1 is related to SQL functions. And if you learn it in week 5 and you do it in week 5, is not enough. So let's do it. Try to finish everything in this week. And that's all about the roadmap and recap. And let's jump into the main content today. So first we are going to learn bags and sets and their operators in Postgres. So sets in SQL is, remember we have learned that the relational model is set-based, and set literals are written like this, and SQL queries are more or less sets of tuples or atomic values. And SQL does provide the normal set operators, which you have seen in some mathematical notations. And however, SQL queries are not exactly working on sets, because for sets, they have two characteristics. The first one is that ordering does not matter in sets. So the ordering of elements doesn't matter in sets. And the second characteristic about sets is that they don't allow duplicates. So there are no duplicate elements in sets. However, in SQL query, sometimes the query results could have duplicates. So they are not strictly sites. They are called bags. And we can convert bags into sites by removing the duplicated data items with the keyword distinct. And of course, SQL support the normal set operators like union, intersection, or except. And these operators, they will produce sets as a result, which means that they will eliminate all the duplicates. However, if we do want them to produce bags, which allows duplicates, we can use the keyword all. So, for example, we can use union all to generate bags, which allows duplicates. So now let's look into the operators of sets and bags. So the first operator, I think we have encountered this operator in some of our examples before. So the operator is called in. It means an element is in a bag, is in a set. And conversely, we can use not in to do the reversed operation. So this is the in operator, which is very straightforward. And there's another operator called exist. So exist is true if and only if the parameter inside this exist is not empty. And do note that in this example we can use subqueries within these operators. So, for example, we can use a subquery as the parameter for exists, and the subquery used here is called a correlated subquery for the main query. So I think the concepts are very straightforward. Let's look into some examples. And if you have your own laptop, you can do it together with me. And let's click on the link. So this is actually the same database we have been using in our last lecture. So there are two tables inside this database. One is called department. The other one is called employee. So an employee can be belonging to a department. And here are some data entries for these two tables. And we can see that this time we have some people having the same name in the same department. For example, in human resources, we have two Alice. So this is the context here, and our question is, can we find the employees who have unique names in each department? So we can think step by step. So let's try to convert this problem into something that we could be described in alternatively, because SQL query language is like describing the data we want. So what's the data we want here? So if we interpret this sentence, we will see that, okay, it's like we should find the employees who should be in, we should find employee who doesn't have another employee with the same name in the same department. We can translate the sentence into this form. So it's like we find an employee who doesn't have, where there's no other employee who has the same department ID and have the same name. So that's how we think about this problem. And if we following this idea, what we can do is we can select from employees where not exist. So there's no other employee who has the same name and who is in the same department. Where not exist. Since we are referring to the same table twice, we need to give them a unique alias inside this query. From E2, select. So there's no other employee who's inside the same department and have the same name. So we should give them the same department. It belongs to, if we go back to the table schema, it belongs to. L2 goes to E2. So where they belong to the same department and they have the same name. E1 dot employee name equals to so it means that there's no other employee who's inside the same department and have the same name as the employee we want to select. So this will give us the employees who have unique names in their department. And sorry, there's a syntax error. We are not exist. Oh, there's one more. We are not. Wait a minute. Oh, exists. Sorry, I typed the wrong keyword. It exists. And we messed up with the second condition here. We should select the employees who have different names. So we should select this one here. So as you can see, we have selected all the employees who have the unique name within their department. And you can see Alice is not selected because Alice has a duplicated name in the same department, human resource department. So this is how we could use exist to help us in some, and plus some queries to help us to do some complex queries. And this is our first example here. And let's move on. So other than in and exists, we have some quantifiers for bags and sets. And the quantifiers, there are two types of quantifiers, which are any and or. So the or operator will return true if all of the subquery values meet the condition. So this is or. And any is also used to compare with each value in the list. And the result will be true if and only if there's at least one row could match the condition. So that's the difference between all and any. Any means at least one, and all means array. So, for example, if we want to find the employees with the highest salary, what we can do is we can select the employee whose salary is larger than or equal to all employees in the table. So this is how all works. And there are more operators on bags and sets. So there are basically three different operators. The first one is union. So union is very straightforward. It's just combining two sets or bags. Intersect is also it also matches the mathematical concept. It means an element appears in both of the sets, and except is different here. Is used to calculate the difference between two sets, and both operands for these operators must be compatible. They must be having the same schema. So if we want to union two different relations with different schemas, we can do that. And the semantics of union and intersection are very straightforward if they just follow the mathematical definition. And for except, and for all these operators, they are set operators. They will generate sets. So what if we want bags? Do you still remember what we have covered in our previous slide? So if we want bags, we just use the keyword all. So for example, we can use union all. And the mechanism of except is a bit complex, but it's still quite straightforward. So let's say R except S. It means an element belongs to R but doesn't belong to S. So the order here matters. So for example, let's say what's the result for R except S in these two tables? What's the result? Can you think about it? So the result will give us the elements that are in R but not in S. So it's like R minus S. So this will give us this. The 1A is removed because it's in both R and S, so it is removed. So what's the result of S except R? Since you know the concept here is very straightforward, the result is like this. So notice that 1A is removed again because it appears in both tables. So that's how except works. And in our previous examples, we have covered that we can use some aggregation or aggregators in SQL queries, and normally subqueries are not allowed in aggregation functions, and aggregation functions cannot be used in VR clouds. Cannot be used. These are some restrictions here, and there are actually a lot of aggregation operators supported by Postgres. And if you want to go through a full list of them, you can follow this link. However, the commonly used ones are those mathematical or numeric aggregation operators, which are average, sum, min, and max, and plus a unique aggregation operator which is called COMP. It could be applied to columns of any data. So that's about the aggregation operators. The key thing you need to take note here are the two restrictions. So subqueries are not allowed in aggregation operators, and they cannot appear in VR clouds. Aggregations cannot be used in VR. So let's try out an example here. So we are using the salary, and we are using one single table here, which is called employee. And each employee has an employee ID as the unique identifier. And every employee has an employee name, and they have their salary. And here are some data inside, and we could see that Ivan has actually the highest salary among all the employees. So in our previous example, we have seen that we have shown an example of using all to get the employee with the highest salary. So do you still remember that query? So what's inside the where condition here? So remember, we are trying to use all. So the condition here is like where salary, because we are selecting the highest salary, the employee with the highest salary. So we need the employee's salary to be larger than or equal to all salaries. So this is how it works. So this will give us Ivan, who has the highest salary. This is our previous example of using all, the quantifier. And since we are finding the highest salary, it's quite natural to think about max. So can we do it with max? So do you think this query will work here? Let's comment on this previous one. Do you think this one will work here? No, I see some of you shaking your head. Why not? Because in our previous slide, we mentioned that there are two things you need to take note of. And one of them is that aggregations cannot be used in VR clouds. And this violates this restriction. So let's run it. You can see that aggregate functions are not allowed in VR. So if this one doesn't work and we still want to use max, what can we do? What can we do? actually we can use a subquery. So it doesn't allow us to use aggregate functions directly inside the VR clause. However, we can put it inside a subquery. So what we can do is we can select max salary from so instead of just putting these aggregate functions directly inside the VR clause, we wrap it with a subquery. And this is how we do it. And you can see that it works exactly the same as how we use all here. So remember, for all the SQL queries, you can have different alternative ways of doing the same thing. However, there are sometimes there are the most optimal choice, but most of the time you have different choices. And for your assignment, you can do it with any one of them as far as it works. So this is the example of aggregations. And now let's move on to our next topic, which is about grouping. So remember that what we have learned is that we can use group by inside the select query, and these are and the select and the group by works by partitioning the results into groups and summarize some aspects of the group and output one tuple per group, and the semantic corresponds to the concept here. So as you can see, this is an illustration of how grouping works. And if you are confused with the grouping here, you can open an Excel table in Excel, and you can try to click on the filter button there. It's actually the filter button is doing the grouping for you on an actual table. But here in SQL, we do it with the group keyword. And remember that there are some restrictions for using group by, and there are if we want to use it inside a select query, the attributes followed by following the select must be either applied supplied to an aggregation operator, or it should appear in the group by clause. So the rationale here is that if an attribute is not used as a grouping feature, it's meaningless to display every piece of that attribute. We should display a summary of that attribute if we don't use it as a group label. So that's the rationale here. And remember that this is also what we have learned. Groups can be filtered with the having keyword. And the semantic of having is that it will generate the groups as how it is done in group by, and it discards the groups that do not satisfy the condition specified by the having keyword, and then it applies aggregations to the remaining groups. And that's about grouping, and that's what we have learned. And here's a new concept, which is called partition. So sometimes it is useful to partition a table into groups. So this is the same as group by, and then we calculate results that apply to each group, which is also similar to group by. But what's different here is that sometimes we want to use the results with individual tuples in the group. So the comparison between partition and group by is that group by produces one tuple for each group. So it's like providing a summarization of groups. And partition augments tuples with group-based values. So later on we will show you why we need this with some real-world examples. And it doesn't have those restrictions of group by, so it can use other functions other than aggregations. It can use attributes other than the partitioning ones. So this is the syntax of partition by. So we can see that it is inside the select clause, and it is applied to individual attributes. So let's show you an example of why we do partition. Since we already have group by, why we still need to do another form of grouping? So remember, group by is to generate summarizations for groups, and partition is to augment individual tuples with group-based values. So let's take a look at this example here. So in this example, we have one table, which is called weather. It is used to store the data of city, date, and temperature on that date. And we can see that we have in this table we have stored 3 different cities, and we have stored 3 different dates for each one of the city. And let's go through the questions. So let's have a look at what will this following query give us. So how many rows should we expect from this data here? How many rows should we expect? Yes, I see some of you showing 3. Yeah, we should have 3 rows because we are grouping by cities, and we have only 3 cities inside our database, and this one is to show the minimum and maximum temperature for each one of the city. So let's run this query. As you can see here, we can see this the result, and that's about grouping. And what about partition? Partition by, what will this one give us? So how many rows do we have this time? Notice that the partition by is different from group by. You see, group by is like a standalone clause after the select, and this one is like inside the select. So it's like an augmentation for tuples. So how many rows do we expect this time? Actually 9 rows. As you can see, we are augmenting each row with some group data. So this, for example, if we select one row from this table, we can get the temperature on a particular city on a particular day, plus the minimum and maximum temperature of that city as a reference, as an augmentation. So let's have a look at another example here. So it is an augmentation of of the original tuples. So this time, instead of calculating the min and max, we can calculate the average temperature. So if we just want to imagine if we are building a web application and we fetch data from this table, and for each row, what we can get is we can get the particular temperature, the temperature of a particular city on a particular day, and we can have the average temperature of that city as a reference. So this is why we need partition by, and it is different from group by, and this is why it is different. And let's have a 10 minutes break, and we will continue. And please grab some snacks here. And if you have any questions, you are also free to ask. Hi.
What's the keyboard shortcut you use to uncomment?
Sorry?
What's the keyboard shortcut you use to uncomment?
You can use command slash. You can select multiple lines, yes, and do command slash. I think it's the same for most IDEs. Yeah. Sorry.
I have a question about FD3.
Sure.
The correction 11 is almost the same as question 10. It is. The correction 10 is like as the section that is never being accessed.
All right, let's start the second half of today's lecture. So let's go through more about SQL queries. And this is about abstractions for complex queries. As you have seen in some of our previous examples, SQL, even one single SQL query could be very complex, and sometimes you may get your final answer after trials and errors. So for complex queries, it is often useful to break the query into a collection of smaller queries. So sometimes we can use subqueries, but sometimes we can break them up into a set of smaller queries, and we can define the top level query to use these smaller ones. So there are several ways of doing this in SQL. So the first one is using views. So we can store some intermediate table as views in SQL. And we can use subqueries as well. So there are three different types of subqueries. We can use subqueries in the where clause, we can use subqueries in the from clause, and we can use subqueries in a with clause. And let's go through them with an example. So let's consider a coursework example. So the example here is to get a list of low-scoring students in each course. So the definition of low scoring means below average. So the mark of low scoring student is less than the average mark for the class. And the schema here is just one table. It's called enrollment, which has the course ID, the student ID, and the mark of that student for that course. So our approach here is we can generate a relation or a temporary table that contains the information of course, student, mark, and class average. And then we select just those tuples that satisfies the mark smaller than class average. So the average mark is not across all classes. It's only for that class. So this is the tricky point here. So we need to calculate the average score for each class. So remember what we have learned in the previous example. We can use partition by to calculate the average mark for each course, just like how we calculate the average temperature for each city. So the first step could be implemented with this query here. So we can use this query to generate tuples containing the information about courses, students' marks, and average marks for that course. So this is what we can do for the first step. And for the second step, we can use the different approaches we have discussed just now. So let's go through them one by one. So the first one is we can use views to store the temporary information. So what we can do here is we can create a view to store the data we have retrieved from the first step. And this is done like this. So I believe you are mostly familiar with this. And after we have generated this view, we can select the low scoring students from that view by comparing the mark of a student with the average mark. So this is how we do this abstraction with views, and it's very straightforward. And the second one is we can use subqueries in the from clause. So instead of selecting from the view, we can select from the result of a subquery. So in this case, we can skip the definition of view. So we don't need to define the view, we just put it into the select here. And do notice that the result of the select from is given an alias with the as keyword. So even if this alias is never used again in this query, we still need to give it an alias. So in the subqueries used in from clause, every subquery must have an alias, even if it's not used again. And for the naming of the subqueries, it inherits the attributes from the query. So this is how you deal with the names you should take note of. And another clause we could use here is the with clause, and it's very similar to from. So it's like with alias as a query, a subquery, and then we select from that temporary table. And the restrictions here are very similar to the from clause. So it must provide names alias for each subquery, even if that alias or name is never used again in the query. So we should do that. That's one of the restrictions. And the other one here is that the names of the subquery inherits the attribute's name from the parent or the super query. So you may wonder, okay, we have from, we have with. So what's the difference here? What's the difference here? And we will show you about the difference later. And here, let's quickly go through from what we have summarized from the examples. So here is the summarized syntax for using views to do abstraction. So it is very straightforward. You can create multiple views, and you can select from those views as if those views are tables. So this is the views. And the advantage of using views is that we can reuse views in multiple different queries later on. So we don't have to write subqueries everywhere. And of course we can use from, and this is the summarized syntax for using from. And the advantage of using this from here is that you can see it's very obvious. We don't need to define views, so we can skip the definition of views. That's the advantage. However, if that subquery, the result of that subquery is used twice, let's say we want another query to use the result of that particular subquery, we have to create that subquery again. So, but however, with views, we can simply reuse the previous view. So this is the disadvantage of using these subqueries. And of course, the same goes for with clause. So what you can see here is the summarized version of the syntax for using with. So it's like we can attach multiple subqueries to the with clause. So you may wonder, okay, we have from, we have with, they are doing essentially the same thing. They are attaching subqueries for building complex queries. And what's the difference here? The difference here is that with clause do support recursive queries. So recursive queries are structured like this. So the keyword here is still with, followed by recursive, followed by the name of the temporary relation. And one of them, and inside the query, we normally use union to aggregate results, to collect results, normally the first query doesn't involve the relation we have created with the with clause. So it is like the initial state for recursion. So please try to remember what you have learned in your algorithms. So it's like for recursion, you need to have an initial state. And the initial state here is the first select. And the second select involves the relation, the relation we have declared in the with clause. And it is for updating data. So it's like when you do recursion, you have the initial state, you have some statements to update the state. And the second select here is used for updating the state. And then you can select, and after that, everything is the same as normal with. So just like how you use recursion in normal programming scenarios, recursive selection is useful in the scenarios where we need to traverse multi-level relationships. So the semantic of recursive query here is let's assume we have a definition like this. We have with recursive R, so as Q1 union Q2. So, and Q1 is the base case or the initial state, and the Q2 is the recursive case, or it is used for updating the states. So here is how the recursion works. So the stopping criteria here, you can see that is, well, the working table is not empty, and the working table is initialized with Q1 and updated by Q2. So this is how it works. So it's like we will exhaustively traverse all the items we have gathered until nothing is left. So this is how it works. It is like how you do recursion in some ordinary programming languages, and the concepts are very abstract. And let's look at some concrete examples. So you can do the practice together with me if you have your own laptop. And here, let's think about this example. So we have only one table here, which is called parts. And parts is used to store different parts of a computer. So inside this table, we have, it is actually used to store the relation between parts and their subparts. So we have the name of the part, we have the name of the subpart belonging to that part, and we have the quantity of subparts belonging to that part. And as you can see here, we have a motherboard belonging to a computer, and we only have one motherboard. And we have some RAM chips belonging to a computer, and we have two RAM chips. And we also have hard disks, and that's hard disk is directly belonging to computer. And on the motherboard, we could have CPU, we could have GPU. And for RAM, we have RAM chip. And for hard disk, we have platter as a subpart. So you can see that it is a tree-like or multi-leveled data here. So how can we traverse all the subparts? How can we traverse this table here? We need to use recursive query. So let's think about the problem here. So can we write a query to display the quantity of all subparts given a part name? Say, for example, for computer, can we get the quantity of all subparts for computer? So subpart, the direct subpart for computer, we have three. We have motherboard, we have RAM, we have HDD. And subpart, we have CPU, we have GPU, we have RAM chip, we have platter and transistor. So we need to collect everything into one table. So instead of writing everything from scratch, let's try to do some fill in the blanks. So this is how. So this follows the basic syntax or the basic style for doing recursive query. So as you can see, the temporary table we would like to build is called included part. So we are trying to include subparts level by level recursively. And it should contain subpart, part, and quantity, which is the same as the original table. So we should have one query to set up the initial state, and we should have the secondary query to update the states. So let's think about the initial state first. So let's say we want to get the parts for computer. So what's the initial state? The initial state is we should select everything where the part is equals to computer, right? So we should select the direct subparts for computer. So this is very straightforward. So what we can do is we can select. We need to follow the order here. Subpart. From parts where we select the direct subparts for computer. So this is how we select the first. This is how we set up the initial state and how we select the initial working table. And then we need to update the working table to gradually grab more parts, more subparts, level by level from the original parts table. And what we can do is, because we need to grab the children for a particular part from the same table. So we need to join the same table twice here. We join this. We are joining the same table twice. This is the temporary table here we have, and we need to grab some more data from the parts table. We need to grab data. We need to include more data. And what's the condition here we should have? So how to determine if a piece of data should be included? How do we determine that? We should use this condition to determine that. How should we do that? Actually, what we already have inside the included parts is the parent. We want to grab the child of that parent. So, in this case, in order to grab the children of that, we should set the subpart of the parent equals to the part name of the child. Sorry. So this is the condition here. So we have the parent, we want to grab the child. So we set the subpart of the parent to be equals to the name of the child. So this is how it works. And let's see. As you can see, we have grabbed everything together into one table with the recursive query. So this is how we use recursive query, and this is a concrete example. So now just what you can remember here is you don't have to remember every details of how to write this. You just remember whenever you encounter a multi-leveled, you need to traverse a multi-level data, then you would think about using a recursive query with the with clause. And that's all about the additional SQL queries. And now let's move on to SQL functions. So this is related to our assignment 1, and so what we have seen in SQL so far, we have learned about the data definition language, which is used to define the metadata of a database, and we have learned about we can use some constraints, we can use some query language to retrieve data, and we can use views to store intermediate results. And this is already very, very powerful. However, it's not enough, not powerful enough. So we need more extensions. And there are many directions for making these extensions. So first, we can include new data types. For example, Postgres, they have extended the standard SQL by including some more data types like the JSON objects. And we can extend SQL by introducing some object-oriented features or concepts. And we can extend by introducing some more powerful constraint checking. And we can what else we can do is we can also package or parameterize queries. And later I'll show you why we need to do this. And this is done by SQL functions. And of course, we want more functions or aggregates to be used in queries. And sometimes we want event-based triggered actions. And that will be covered later in this course as well. And for packaging and parameterizing these queries, so why we have the motivation for doing so? So why do we do that? So this is our previous example for using the recursive function, using the recursive query. So we have specified the root part as computer here. So what if we want to change the root part of the computer? So do we need to copy the whole chunk of query to another place and change just one place, just the root element there. That's a waste of space. That's a waste of code. So, in order to improve the reusability and readability of our SQL code, we need to package and parameterize queries. So this is why we need to do this. Why we need to do query parameterizing. And there are two concepts related to this purpose. The first one is called stored procedures, and the second one is called stored functions. And we will go through both of them. And stored procedures or functions are small programs. They are stored in the database, and they are invoked in SQL queries. And Postgres supports three different types of stored functions or procedures. The first one is called SQL functions. The second one is PLPG SQL, which is to add in some procedural features, like some control flows into the SQL script. And it also supports Python scripting. So today we will cover the SQL functions. So this is the grammar of this defining a function. So you can omit or replace these two keywords there. So it's like create or replace function followed by the function definition. So the function. So remember what you have learned in C. So in C language, every function is associated with a prototype of that function, and this prototype of function is similar here. So it's just a function name followed by a set, or it's actually a list of parameter names and parameter types, and we also need to return. We also need to specify the return type, because in SQL. An SQL function or stored function is expected to return something. So this is how we create the hiding part of the function, and then it's followed by as and $sign, a set of SQL statements, and we should specify the language as SQL. So within the function, if sometimes we can, when in the prototype of the function, sometimes we can omit the argument or parameter names, and if they are ignored, they can be accessed via $sign plus numbers here. Do note that in SQL the number starts from 1, but in normal programming language the number starts from 0. So, and the return value here. So the result is, by default, is the result of the last SQL statement. And the return type could be any Postgres data type. And remember, we could have some customized data types. We could declare some customized types. And sometimes, if nothing is returned, we can return void. And return types could, if we return tuples or tables, return type could be defined as set of some type followed by a table name. Or if we are customizing the returned tuple or returned attributes, we could use returns without set of, returns table followed by the columns, the customized columns or attributes. And if we want to invoke a function, we can just use select, the keyword select. And let's go through an example here. This is the same example as what we have used for the recursive query. So this time we have the correct answer for the recursive query, and the results are here. And let's go through the questions. So first, how can we turn our previous query into a function? So I have already finished the hiding part. So I finished everything before as you can see here, we can use return set of a custom return type. This is a customized type we have defined because we don't have a table. We don't really have a table containing subpart and quantity, and we have to return something that contains this. So this is why we need to use a customized type here. This is something you should take note of, and let's start creating this function. So what we can do is we can copy this whole chunk of function here, and let's comment out. So what do we need to change? We need to change something, right? So we need to replace the root element, the name of the root element, with the parameter of the function. And that's it. Remember, we can invoke functions with select, and functions could be used just like tables. So this is an interesting part. So you can select it like a table, or you can just use select to invoke it, because sometimes functions could return null, and it's meaningless to select like a table from a void value. So that's why we could just use select to invoke that function, or we can select it like a table if we know that it will return. It's not returning void. So let's run this. As you can see, we can select all subparts from computer, and we can select all subparts from a motherboard. And you may notice the different notions here printed out by Postgres. It's because of the different ways of invoking this function. The second one is just like an ordinary table. So this is an example of SQL functions. And let's try to do some small modifications here. So what if we don't want to use the customized type? We don't want to define this customized type, but we still want to return this the two columns which doesn't correspond to any table. So remember, in our slides we have mentioned that we can return table. We can return a table header here, and we can return text and int. Since we are returning author varchar, So this will essentially do the same thing. So if we don't use this type in multiple places, we can just do it locally here. So we can just return a customized type of tuples. Sorry, here's a syntax error near varchar returns. Let me double check. I don't think there's anything wrong. Wait. Let's see. Subpart quantity. And this will give us the same thing. So what we can do is we can do something similar to when we create a table, but without a table name. It's just like a lambda function in Python, or maybe an anonymous function or anonymous table here. So this is what we can do. So without using setoff, without using a customized type. And another small change we can do here is assume we don't have this parameter name specified in the function prototype. How can we refer to the parameter in our? How can we refer to this parameter here? So what we can do is, it is also in our previous slide. We can use the $sign plus a number here to refer to this $sign plus 1 refers to the first parameter of the function, and this function only has one parameter, so we just use $1 and it will give us the same result. And let's run it. So as you can see, we have multiple ways of doing the same thing here. So these are some details about SQL functions. And now let's move on to our last concept today. So it's called SQL procedures. So the creation of procedure is very, very similar to creation of function. And actually the concepts of them are similar as well. So the procedure is actually a collection of SQL queries. And the syntax for creating is just create procedure. And you don't need to specify the return type, because in SQL, logically, the start procedure are not expected to return any value. However, if you really want to return some value with start procedure, you can use the returning keyword, and it is within the $sign. So that's the difference between the syntax of declaring functions and procedures. And procedures are invoked by call. It's different. So remember, functions are invoked by select, and they could be used essentially the same as tables. So you may wonder, okay, we already have functions, why do we have procedures? So what's the difference between them? Why should we use them in different scenarios? So here's a list of differences, and you don't have to memorize all the differences here. So you should only take note of the key differences. So the first one is the purpose. So start procedures are not expected to return any value, and functions are expected to return values. So that's the first one. And the second one is followed by the initial purpose. So since start procedures are not expected to return any value, we can use the keyword call to invoke the procedures, the start procedures. So inside the procedure, we can do update, we can do delete, so we don't need to return anything. So we use the call keyword to invoke procedures. And since functions are expected to return some value, so we can treat functions as tables. So we use the keyword select to invoke functions. So functions are treated as tables because they are expected to return a set of values. So that's the difference between procedures and functions. So that you don't need to remember everything here. So you need to remember the 2 key points. And that's all for today's lecture, and thank you for attending. Please do remember to do your quiz 3 this week. But I think all of you here must be doing the quizzes. But still, there are about 10% of students not doing any quiz. And yeah, it's like every term there are about 10% of students not doing any assignment.